Alrighty, lads and ladies, welcome back to Calc 2. Today, we are going to wrap up section 7.4 on partial fractions that we introduced on Monday. Monday, I was able to show you a few simple examples, things where the setup is sort of as nice as possible because the denominator downstairs factored into distinct linear factors, right? Non-repeated linear factors. Today, we're going to explore what happens when you have repeated factors downstairs and also irreducible quadratic factors downstairs, both of which can complicate the partial fraction setup a little bit. And because the setup is thrown off by those, the procedure for solving for the coefficients can be made a little bit trickier also. Let me fire up the document camera, get some fresh paper out here, and we can get rolling. Oh. Okay, here we are. So this, of course, as always, is MAC2312. Section number 004, which is a Calc 2 class. And the date is fun today. It's 2/2/22. Today, we will finish partial fractions. Which is section 7.4. That's the main thing. I will begin by sort of reminding you what we've said so far. Let me just pop open your book so I have a ready source of examples. So I'll say, recall our PFD Bible. This says if the denominator has a factor looking like something here, then the PFD setup must contain whatever I put here. So we said if we have a simple linear factor, something like ax minus b, then your PFD setup must contain a constant over that simple linear factor. If you had a repeated linear factor, then your PFD setup had to contain a bunch of terms, however many, like whatever this power is, you're going to have that many terms in your PFD setup. And the way we wrote this was like a over ax minus b plus a2 over ax minus b squared. And you build all the way up to whatever that power is. This. It is also possible that you have an irreducible quadratic and in that case, your PFD setup will have to have a linear term. And then you could have an irreducible quadratic that is repeated. And then you'll need m terms, just like here, but each of them looking like this. So that would lead to something like a1x plus b1 over ax squared plus little bx plus little c plus a2x plus b2 over ax squared plus bx plus c all squared. And you'd build all the way up to whatever that power is. Like this. Okay, so this is sort of the, the table or key that tells you how to set up partial fractions for a given proper rational function. The things that I want to tackle today that we haven't really tackled yet are these cases, right, which are sort of the nasty ones. And also, so today we will practice with the bottom three cases. And talk about what to do if the rational function is not proper. Now remember, a rational function is called proper if the degree of the top is strictly less than the degree of the bottom. So if you're given a rational function to integrate, and the degree of the top is the same as the degree of the bottom, or the degree of the top is bigger than the degree of the bottom, then you can't do any of this. All of this presupposes that your rational function is proper. So I want to begin with this. You have some problems in your homework that address this issue, and you may have kind of worked your way through that already if you're trying to be super on top of your stuff. But I'd like to begin just with an example there, because let me annotate here. What this requires is long division. Not long division of numbers, but long division of polynomials, right? And that is something that you see in pre-calculus, depending on what your pre-calc class is like. You may or may not have gotten a good exposure to it, but I will remind you how to do that now. So let's get to it. Let's look at an example. So I want to evaluate the integral of x cubed plus x over x minus 1 dx. Here I am integrating a rational function, right? This function inside here is rational because the top is a polynomial and the bottom is a polynomial. So this falls into section 7.4. The degree of the top is 3. That's the largest power of x I see anywhere there. The degree of the bottom is 1. So this is not a proper rational function. So I'll say f of x equals x cubed plus x divided by x minus 1 is an improper rational function. Therefore, we need to long divide. Now, in this special case here, where the denominator is linear, just a single linear factor, you could get away with synthetic division instead of long division, if you remember synthetic division. But I'm going to teach this with long division because that's the more general case. If your denominator was more complicated, you would need long division. So let's do it. This is a lot like an improper fraction in the sense that you learned in elementary school, like 5/3 is an improper fraction, right? Because the top is bigger than the bottom. And in elementary school, you learned how to write improper fractions as mixed numbers by dividing the top by the bottom, right? Same thing here. We're going to rewrite this improper rational function as the function version of a mixed number. So the function version of a whole number is a polynomial, and the function version of a fraction, a proper fraction, is a proper rational function. So our goal is to rewrite this improper rational function as a polynomial plus a proper rational function, and long division is the tool that does that. So how do you long divide polynomials? How do I take this numerator and actually carry out the division here and divide it by x minus 1? Well, the answer is first you write down the numerator, and I recommend inserting any missing terms here. So like there's no x squared term, there's no constant term. So I'll write that, leave some space on the left over here, leave lots of space below. And I'll write this as x cubed plus 0x squared plus x plus 0. And then I'm going to write a big division bar just like you did in elementary school. And over here on the left, I'm going to put the divisor, the thing you're dividing by. Now, the way this works, you divide this polynomial by paying attention only to the leading terms. So I'm going to give you kind of an algorithm, a set of steps that you loop over and over again. And the key is that at each loop, you pay attention only to the lead term. So I ask, what is x cubed on its own divided by x on its own? Or in other words, what polynomial can I multiply x by in order to turn it into x cubed? And you would say?
X squared.
My volume up.
Of this podcast.
Oh, sorry. There we go. Okay. Amanda, what was that?
X squared.
Yeah, exactly. X squared. So I put an x squared up here, right? Because when I multiply x by x squared, it'll turn into x cubed. So the result is going to appear on the top here. Then I'm going to take this x squared and distribute it to both of these terms here, all of the terms over here. So x squared times x is, I'll write the answer down here, x cubed. X squared times -1 is minus x squared. And then we're going to take these whole rows and I'm going to subtract the whole bottom row from the row above. So I always like to put this in parentheses and put the negative here. That reminds me that I'm subtracting this whole thing from this whole thing. X cubed minus x cubed is 0. So here there's like a 0. I'm not going to write it. 0x squared minus negative x squared is positive x squared. We're subtracting a negative. And then I've got x minus nothing, that's x. And I've got 0 minus nothing, that's 0. I'll just leave it like this. Okay, so that's one loop of this division algorithm. And we're going to run through this over and over again until we're done. So I start back over. I say, look at the lead term here and the lead term here. What should I multiply x by in order to turn it into x squared?
X.
Yeah, just x. So up here, I'm going to write plus x. And then I distribute this x, just this x, over these two terms, and I write the answer down here. So x times x is x squared. X times -1 is minus x. And then just like before, put a line, parentheses, subtract. Any questions so far? All right, then, carrying out the subtraction, x squared minus x squared is 0. X minus negative x is 2x. One more run. To turn this into this, I would multiply by 2, so I put a plus 2 up here. Carrying out the multiplication, I get 2x minus 2, line, paren, subtract. 2x minus 2x is 0. Nothing minus -2 is positive 2. This is now done. One question I get a lot from pre-calculus students when I'm teaching this is, how do you know when you're done? And the answer is when the degree of the thing you get here is smaller than the degree of the thing you get here. In other words, when there is no polynomial, you could multiply this by in order to turn it into this. To turn an x into a 2, you'd have to multiply by 2 over x, or 2x to the -1, which is not a polynomial because the power of x is negative. So we're done. That's when we stop. This term down here is called your remainder, just like in elementary school, right? Like 10 divided by 3 is 3 with a remainder of 1. This is your remainder. This thing up here is called your quotient. This is the answer. So the way you would write this is you would say x cubed plus x divided by x minus 1 is equal to x squared plus x plus 2, but with a remainder of 2, which means you've still got this 2 over x minus 1. All right, this part is not cleanly divisible by x minus 1, so you just have to write it as 2 over x minus 1 left over. Which means that your integral of x cubed plus x divided by x minus 1 dx is equal to the integral of these things. And I will split that integral up because the integral of the first piece is done differently than the integral of the second piece. This first piece is just straight power rule stuff. It's very easy. How do you do this piece? Is there another way to do this? Sorry, so question in chat. Is there another way to do the division here? You could have done synthetic division for this special case because the thing we're dividing by is of the form like x minus a constant. But in general, no. In general, this is the only attack that will always work. I do have links if you want in the modules. If you look under the review material in modules, there's a link there for polynomial long division if you want to remind yourself how to do this, if you want more practice. This is the only example like this that I'll be doing today. But if you do look in our modules under the review material, I believe, yeah, right here, Patrick JMT video polynomial long division, and then another one, a harder example. So that and also this. So I've got 1, 2, 3 links here if you need to go back and review how to divide polynomials a little bit more. The answer came in chat. Yeah, this is a u sub thing. So here I could I'll use u be x minus 1, and du would be just dx. The first piece I can integrate right away. That's x cubed over 3 plus x squared over 2 plus 2x. I'm not going to write the plus c yet because I'll still have this. I can pop this 2 out front, and I'll have integral 1 over u du, which is going to be a natural log. That's x cubed over 3 plus x squared over 2 plus 2x plus 2 times the natural log absolute value of u plus c. And then finally, we know that u is x minus 1. So at the end of the day here, we get x cubed over 3 plus x squared over 2 plus 2x plus 2 times the natural log of the absolute value of x minus 1 plus a constant. And that's your final answer. So the integration step is not that bad. And this is kind of the running theme in section 7.4. There's a lot of algebra, and then the integrals at the end are quite easy. I will show you one example today where the integral at the end requires a little bit of careful love. But for the most part, this is how 7.4 goes. Questions on any part of this procedure? The division, knowing to divide, right? Everybody's comfortable why we had to long divide. Sure, so two things. How do we know we get a natural log here? Well, the integral of 1 over x dx or 1 over u du will always be the natural log of u. Right, so this step is because we know that the derivative of the natural log of u is 1 over u, which means that the integral of 1 over u is natural log of u. If you have more complicated stuff downstairs, like x squared minus 1 or something like that, that won't come out to a natural log, at least not right away. You need to do the substitution. So when we look at this guy, I see, oh, well, the bottom is just x minus 1. So let's try to substitute for that. And when I do that, also popping out the 2, the constant 2, I get 1 over u inside. That will always integrate to the natural log of u. And then the other question was, can we remind ourselves why we had to do long division? It was because this was an improper rational function, and improper. So anytime you have an improper rational function, you must do long division. Improper means that the degree of the top is greater than or equal to the degree of the bottom. So remember, rational functions, we're always talking about polynomials over polynomials. The top and bottom will both be a polynomial. Every polynomial has a degree, right? An integer, a non-negative integer that is the largest power of x. The degree of the top here was 3. The degree of the bottom here is 1. So since the degree of the top is bigger than the degree of the bottom, we know this thing is improper and therefore must long divide. So anytime you are given an improper rational function to integrate, you will always long divide. Other questions on this one? Okay, let's grab something a little more challenging, shall we? Let's look at something where we have an irreducible quadratic factor. Did we do this last time? Well, we did not. In the interest of time, here we go. Let's do this. We're going to do example 5 next. I'm just going to write this down. Want to evaluate the indefinite integral of 2x squared minus x plus 4 over x cubed plus 4x dx. The degree of the top is 2, right? It's a quadratic. The largest power of x here is 2. The degree of the bottom is 3. So this is a proper rational function. So we don't have to do any long division here. So instead, what we're going to do is we're going to begin by factoring the bottom. The numerator 2x squared minus x plus 4 is just chilling. That denominator can be factored as x times x squared plus 4. The factor x squared plus 4 is an irreducible quadratic. What does irreducible mean? Why would I have to do something special for this? Cannot simplify is a reasonable thing to say, specifically cannot factor. At least not using real numbers. The truth is, if you're willing to use complex numbers, there's no such thing as an irreducible quadratic. But in this class, we're going to focus our attention on real numbers. We're not going to be worried about using complex numbers in our algebra steps. So x squared plus 4 cannot factor, which means when I think about what terms in the PFD setup could have contributed to this guy being downstairs, it's not just a constant over him. It's any proper rational function who has this as its denominator. And since the denominator, if you're just looking at this factor, would be quadratic degree 2, that means you have to allow for the numerator to be not just constant, but linear. So your setup, your PFD setup is 2x squared minus x plus 4 over x times x squared plus 4 equals. The x here is a simple linear factor, so he just gets one term with a constant upstairs. X squared plus 4 is an irreducible quadratic, so he gets a linear numerator. That's the idea. Okay, and this is just following the rule in the PFD setup Bible, right? Following this piece right here. From here, everything's going to go the same way it did on Monday. We're going to clear out those denominators. We're going to combine like terms. We're going to get whatever we can using the Heaviside trick, and then we'll set up a linear system to solve for the rest. Really quick, before I wander away from this, how do you test if something is irreducible? With a quadratic, you just check the discriminant. If b squared minus 4ac is less than 0, then that quadratic doesn't have any real roots, which would imply that it is irreducible. Here, a is 1, b is 0, c is 4, so 0 squared minus 4 times 1 times 4 is negative 16. And negative 16 is less than 0. So yep, even if you didn't know through other means that that is irreducible, you can figure it out by checking the discriminant. And if you're ever wondering, is the quadratic I'm working with irreducible? Can it not be factored over the real numbers? You need to check to see if the discriminant is negative. If the discriminant is negative, then yep, that's irreducible. All right. Next step is to clear out the denominators. So I'll have 2x squared minus x plus 4 on the left. I'm multiplying everything here by x times x squared plus 4. That's what we're doing. When I multiply a over x by x times x squared plus 4, the x's cancel and you get a times x squared plus 4. When I multiply bx plus c over x squared plus 4 times x squared plus 4, the x squared plus 4's cancel and the x's survive. So I get plus parentheses bx plus c times x. I want to pause here for a minute, make sure we're all comfortable up to this step. Meaning like comfortable with this factoring, comfortable with this being irreducible, comfortable with this setup, and comfortable with the algebra that gets us here. Are there any questions about any of those steps? I multiply x times x squared plus 4 on both sides. So I'm multiplying both sides by the denominator. So on the left-hand side, the denominators cancel perfectly, and I'm just left with this top. On the right-hand side, when this piece gets hit by these factors, the x's cancel, and I just have a times the piece that doesn't cancel. When this piece gets hit by these factors, we have to remember that the tops and bottoms of fractions are always in these implied parentheses. So the x squared plus 4 will cancel here, and I'll have bx plus c times x left over, like this. And these parens are important. If you forget these parens, you'll get into trouble. All right. This is the equation that I was calling star yesterday, so I will label this as star. And it is at this step where we can use the Heaviside trick to recover as much as possible. So is there a number that would be really nice to plug in to star? A number that we can plug in for x in this equation that will make a lot of stuff go away at once. Yeah, very good, 0. If I plug in 0 for x, then in this side, since I have an x times this whole thing, all this shit will go away. And I'll just be left with a's and numbers. So if I evaluate this at x equals 0, I get 2 times 0 squared minus 0 plus 4, which is just 4, equals a times 0 squared plus 4, which is 4. This whole thing goes away because you'd have 0b plus c times 0. Dividing both sides by 4 here, you get a equals 1. Here's the bad news. In the problems we were solving on Monday, we were able to get all of the constants using the Heaviside trick. Not here. Because there is no nice number you can plug in for x that will make this factor 0. That's what irreducible means. So there's nothing I can do to make this go away. There's no number I can plug in for x that will make this go away. That's a slight lie. If you're comfortable working with complex numbers, you could plug in 2i. That would do it. But for us, this is a class about real numbers. So having done this, the game is to update the equation star by plugging in 1 for a, and then multiplying everything out and setting up a linear system. So this will become 2x squared minus x plus 4 equals 1 times x squared plus 4 plus bx plus c times x. And now I'll multiply out the right-hand side. So I'll have x squared plus 4 plus bx squared plus cx. X plus 4 equals, now I'm going to collect the x squareds together. I've got 1x squared and bx squared here. That's 1 plus bx squared. I only have the single x term, that is cx, And then I have the constant term here, 4. And now we play that game like we did at the start of class on Monday, where we said, the coefficients have to match. So the number attached to x squared on the left is 2. The number attached to x squared on the right is 1 plus b. So this tells me that 1 plus b has to be equal to 2. The number attached to x on the left is -1. The number attached to x on the right is c. So c must be equal to -1. And it's silly to say, but the constant on the left is 4. The constant on the right is 4. So 4 equals 4. We'll do it. Why not? This is a 3×2 linear system. It is easy to solve. If 1 plus b is equal to 2, then b is equal to 2 minus 1, which is 1. And this guy just straight up says c is -1. So now we're done. Now we know a, b, and c. You can go straight to doing this stuff without doing this stuff, but this stuff saves you a lot of time. If you just went straight ahead, multiplied everything out, and set up the linear system, it would have a, b, and c. And you'd have more work to do to solve the system. So you should always do this thing, which is called the Heaviside trick. Named after Oliver Heaviside, the man who discovered it, to recover as many of the coefficients as you can before resorting to the linear systems approach. Okay. Any questions up to the linear system? So questions on the Heaviside trick or any of this algebra? Any questions on how we get from this equation to this system of equations? Do we all see where the 1 plus b equals 2, c equals -1, and 4 equals 4 come from? Okay. Then we're ready to do our integral. Remember, our goal was to integrate this function. We come back here. So we had 2x squared minus x plus 4 over x times x squared plus 4 equals a over x, and a was 1. So this is 1 over x plus b was +1, so that's x. C was -1 over x squared plus 4. So plugging in, a equals 1, b equals 1, c equals -1. We get this. So the integral of the function on the left, which is the integral I want, is equal to the integral of the function on the right. And the function on the right is not terribly hard to integrate. I can certainly split this up as the integral of 1 over x dx plus the integral of x minus 1 over x squared plus 4 dx. The 1 over x integral is easy. How do I do the x minus 1 over x squared plus 4 integral? Very good. Everybody see the suggestion in the chat? We can split it up as x over that stuff minus 1 over that stuff. So I'll have here, I'll just write it. This is the natural log of the absolute value of x. That's the integral of 1 over x. Plus the integral of x over x squared plus 4 minus 1 over x squared plus 4 dx. Again, here I'm using the algebra rule that a plus or minus b over c is a over c plus or minus b over c. Very useful little algebra trick. It's like the dumbest thing in the world when you look at it like that, but when you look at it like this, it's like, oh, okay, that is useful. So now we just need to figure out how to integrate x over x squared plus 4. So I can split this up, of course. All right, so now ln absolute x plus integral x over x squared plus 4 dx minus integral 1 over x squared plus 4 dx. One of these should be very, very fast. Well, I mean, one of them you don't need to do any work on. The other one you do need to do a little bit of work on. What is this? Very good. This is an inverse tangent. So we proved the formula. Integral 1 over x squared plus a squared dx equals 1 over a times the inverse tangent of x over a plus c. This is something we proved in 7.3. It's a trig sub thing. So this guy is going to be 1/2 times the inverse tangent of x over 2. Right? Because this 4 is 2 squared. How do you do this guy? Very good. This is a substitution. So to solve the middle integral, purple pen. Solve the middle integral, we're going to substitute z equals the bottom. Because when you do that, dz is 2x dx. So I have an x dx upstairs here. That is going to be dz over 2. So what we get is the natural log absolute value of x plus 1/2 integral 1 over z dz. That's the middle integral after that substitution. Minus 1/2 inverse tangent of x over 2. I'm leaving off the plus c because I still have an integral here. I can do that. Finally, the integral of 1 over z is the natural log of the absolute value of z. This is plus 1/2 ln absolute value of z. And then I've got my minus 1/2 inverse tangent of x over 2. And I'll write a plus c at the end here. And my very last step is to plug back in this z. So this is the natural log of the absolute value of x plus 1/2 natural log absolute value of x squared plus 4 minus 1/2 inverse tangent of x over 2 plus a constant, and we're done. So the integration steps here, still not too bad. Still not too bad. A little bit of algebra to split up. And in order to even realize that the right thing to do with this is to split it up like this, you kind of want to have this in your head, right? This is one of your like known integrals. It's one of the things that we should be able to pull right out of the air like nothing. So when you see something like this, your first thought should be, oh, well, 1 over x squared plus 4. I know exactly what to do with that. So I'm going to split it up, and then I'll figure out what to do with the other piece. And this other piece turns out to not be bad, right? It's just a little u sub or z sub. That's the result. Questions up to this line? Questions to the bottom? Okay, I'm going to make a little comment on notation. Notice, even though this is like a problem in 3 pieces, I'm maintaining an unbroken chain of equal signs here. All right, I'm not like leaving this off to go work on this or this separately. This is the sort of organizational structure that you want in your work also. And so I recommend, as you solve these problems, mimic what I'm doing here. Keep your shit organized. It will really, really help your thinking. Okay. Irreducible quadratics, not the end of the world. Repeated irreducible quadratics are also a thing. So let's look for something one slight level higher. Yeah. Okay. We're going to do this example. And these problems are somewhat long. This might take the better part of the rest of class. Here's what we're doing. They factored the bottom already for us. That's quite nice of them. What is the degree of the top?
Three.
Good, 3, right? The top is a cubic polynomial. The largest power of x up there is 3. What's the degree of the bottom? You gotta think a little more about this one, right? If I multiply out x squared plus 1 all squared, that would be x to the 4 plus 2x squared plus 1. Yeah, good. So this piece right here, just this piece is degree 4. When you distribute this x, it would become degree 5. So the denominator is degree 5. The numerator is degree 3. 3 is strictly smaller than 5. So we don't need to do any long division here. We're going to begin with the PFD setup. I'm going to write the numerator in the normal order, negative x cubed plus 2x squared minus x plus 1. Denominator here is x times x squared plus 1 all squared. And according to my PFD setup Bible, here we go. X squared plus 1 is an irreducible quadratic. The roots are plus and minus I. So this is a repeated irreducible, which means not only do we have one linear numerator, we have to build up to this power here, which is 2. So he will contribute, let's see, so this x is going to be just a over x. Then this irreducible quadratic, which is repeated, will give me a bx plus c over x squared plus 1 plus dx plus e over quantity x squared plus 1 squared. That is the correct partial fractions setup for this function. Questions on where this setup is coming from? Oh, sorry, coffee grounds got to the bottom of my giant cup of coffee. Whew, that's bad. All right, if we're all comfy with this setup, the next step is to clear out all the denominators. So on the left-hand side, I'll just be left with the numerator, negative x cubed plus 2x squared minus x plus 1. On the right-hand side, a over x, the x will cancel, and I'll have x squared plus 1 quantity squared. The bx plus c term, one of the x squared plus 1 will cancel, so I'll get bx plus c times x squared plus 1. In the dx plus e piece, both of the x squared plus 1s will cancel, and I'll just get dx plus e times x. I suppose I should say this piece, x squared plus 1 is irreducible because the discriminant here is 0 squared plus 4 times 1 times 1 is negative 4, right, which is negative. So we have not just an irreducible, but a repeated irreducible. So here's the setup. Here's the setup after we clear out the denominators. And it's at this stage that we apply the Heaviside trick. Is there any number that is nice to plug into this? Well, this piece has a factor of x here. This piece has a factor of x here. So if we, yeah, exactly. If we send x to 0, we'll get 0 plus 0 minus 0, 1 equals a times 0 squared plus 1 all squared, plus all the other stuff is 0. Which just means a is 1. Unfortunately, that's as much as we can get from this. Heaviside takes us no further because there is no number I can plug in to make this go away or to make this go away. So from here, expand everything out, plugging in 1 for a. So this would be 1 times x squared plus 1 squared, which is x to the 4 plus 2x squared plus 1, plus we've got some algebra to do here. I would treat this as bx plus c times x cubed plus x, and then FOIL it. So you get bx to the 4 firsts. Outers are bx squared. Inners are cx cubed. And your last is cx. And then this piece, when you distribute the x, you get plus dx squared plus ex. Now we will combine all the like terms, meaning we're going to put together the different powers of x. Over here, I'll still have my left-hand side, negative x cubed plus 2x squared minus x plus 1. Over on the right-hand side, I have a 1x to the 4 and a bx to the 4. So it's 1 plus b times x to the 4. Now I go looking for x cubes. I have a cx cubed. Nowhere else do I have an x cubed, so plus cx cubed. Now I look for x squared. I have here 2x squared, here bx squared, and here dx squared. So that's plus 2 plus b plus d x squared. Regular old x's, just ex. And then constants, terms without any x's, just this one. And now we equate coefficients on both sides. The coefficient of x to the 4 is 1 plus b on the right, and the coefficient of x to the 4 on the left is 0. There are no x to the 4s. So 1 plus b is 0. The coefficient of x cubed on the left is just c. The coefficient of x cubed on the cx. Did I leave a cx term out somewhere? Oh, yeah. Thank you. Cx and ex, sorry. So this should be c plus e times x. Thank you. Save me there, Misty. Yeah, cx plus ex. So on the left-hand side over here, there are no x to the 4s, right? The highest order term is x cubed. So I can think of there's being an x to the 4 term here. It's just that the coefficient is 0. Kind of like we did when we inserted the missing terms before our long division. Anything that wasn't there, it's really there. It's just that the number in front of it is 0. Same thing going on here. I don't see any x to the 4s. Well, that means that there's 0 of them. And it just helps us match things up. The next piece I'm going to look at are the coefficient of x cubed, which on the left-hand side is -1, and on the right-hand side is c. So c equals -1. Then the coefficients of x squared. I have 2 plus b plus d. And on the left, I just have 2. Then the x's, I have a c plus e. And over here, I have a -1. And then the constants, I have 1 equals 1. So this is a pretty big system, but most of the equations are very, very simple. This first guy is says b is -1. The second guy says c is also -1. This guy might look a little bit daunting at first, but then you remember b is -1. You can start by subtracting the 2 over, and you get b plus d equals 0. Then plugging in -1 for b, you get -1 plus b equals 0. And adding 1 to both sides, you get d equals 1. Finally, c plus e equals -1. You know c is -1. So this means -1 plus e equals -1. Adding 1 to both sides, you get e equals 0. So really not a bad system to solve. We got A from the Heaviside trick. B, C, D, and E all fall neatly out of the resulting system. No real work. No elimination, no matrices, no nothing. Questions so far? Okay, then let's go back, plug everything in, and see if we can do the integral. Fresh paper. So what did we have? Let me just write this down. We're going to come back up here. And we're going to plug those values in. And I'll get -x cubed plus 2x squared minus x plus 1 over x times x squared plus 1 squared equals a over x, where a is 1, that's 1 over x. So again, we'll get a natural log from the antiderivative of m. B and c are both -1, so this is plus -x minus 1 over x squared plus 1. D is 1 and e is 0, so this is plus x over x squared plus 1 squared. Which means that the integral of -x cubed plus 2x squared minus x plus 1 over x times quantity x squared plus 1 squared dx is equal to the integral of 1 over x dx plus the integral of -x minus 1 over x squared plus 1 dx plus the integral of x over quantity x squared plus 1 squared dx. Well, if you remember, the original function was 1 minus x plus 2x squared minus x cubed. So I'm just rewriting this in the standard order, which is -x cubed plus 2x squared minus x plus 1. So our task is now each of these integrals. The first one is certainly very easy. It's the natural log of x. How do I do the second integral? It's a trick we've used already today once. Good, we'll split it up. So I'll write this for now as plus integral of negative x over x squared plus 1 minus 1 over x squared plus 1 dx, like that. How do I do this last guy? Integral x over x squared plus 1 squared dx. So the middle guy, we're going to split him up like this. What about this guy? I'll give you a hint. We could have given you this back in Calc 1. Another hint, it's the same thing you do to integrate this piece. Maybe I'll go ahead and just write out the next step where we actually split up this integral. This would be minus integral x over x squared plus 1 dx minus the integral of 1 over x squared plus 1 dx plus the integral of x over quantity x squared plus 1 squared dx. The second and the fourth thing require the same trick. It's a little substitution. I'll use z here and w here just to avoid things getting confusing. You don't want to use the same variable in two different substitutions. This guy is going to be inverse tangent. Right, that's just a known thing. So I'll have natural log absolute value of x minus 1/2 integral 1 over z dz. Right, x squared plus 1 is z, x dx is 1/2 dz, so the 1/2 comes out, minus the inverse tangent of x plus integral. Here, same sort of thing, w equals x squared plus 1, dw is 2x dx, x dx is 1/2, 1/2. And then you have 1 over w squared dw. The 1 over z we know is going to be a natural log. So this is ln absolute x minus 1/2 ln absolute z minus the inverse tangent of x plus 1/2. What is the antiderivative or indefinite integral of 1 over w squared dw? So 1 over w squared is w to the negative 2. And if you apply the power rule to that, you get w to the negative 1 divided by negative 1, which is negative 1 over w. Now I write my plus c because there are no more integrals. The last thing we do is plug back in for z and for w. So we get the natural log of the absolute value of x minus 1/2 natural log of the absolute value of x squared plus 1 minus the inverse tangent of x minus 1/2 times 1 over x squared plus 1 plus c. And that is the end of the day. Okay. So these can get a little tricky. This was a good sized partial fractions problem, right? This is not something that was just like immediate for sure. I'd like to point out that not everything comes down to a natural log. That's important, right? It's easy to get in our heads that like, oh, it's always going to be natural logarithms. That's not true, right? This was an inverse tangent. This turned out to be a power rule thing. So you do need to be careful. Don't move too fast. Slow down and think about stuff as you go. Yeah, not every term from partial fractions will give you a natural log. In the last few minutes here before I let you go, I want to show you some stuff that it's a question in a DM. Would this be a test question? Not the whole thing, no. I could give you this function and ask you for the partial fractions setup, like just giving you this and asking you to set up the PFD but not solve it. That's something I could do. I could give you this function after doing the PFD and ask you to integrate it. Like I could ask you to integrate these things all on one problem on a test. That would be fair. But asking you to do both of those things and solve the linear system all in a single problem, that would be too much. That's too long for a single test question. But any part of this could be a fair test question. So I could give you this first bit here and say, finish the problem. Or I could give you just this function and say, set up the partial fractions. Or I could give you the partial fractions setup and say, find A, B, C, D, and E. Any one of those things on their own would be a fair test question. But the whole thing altogether is too much. All right, I want to show you a few fun problems that don't look like partial fractions problems at first. You have some things like this in your homework and study guide. So before we walk away from 7.4 entirely, what is it? EDX plus 1. Here's a funny looking integral. Can I do partial fractions on this? Should be a resounding no, right? This is not a polynomial. E to the x is not a polynomial, it's exponential. So no, cannot do partial fractions on this. Do we know how to do this any other way? Also no. There's nothing that I can do nice with this fraction. You can't split up, like fractions don't split up over their bottom, they only split up over their top. What you do here is make a little substitution, and that substitution will turn this into a partial fractions problem. The substitution is quite subtle. Z equals e to the x. The thing is, normally to make a substitution go through, you would need the differential piece, right? And there is no e to the x upstairs here. But I can introduce one. couple ways to do this. I could say, okay, so integral 1 over e to the x plus 1, I can multiply by e to the x over e to the x. And then I can group that as 1 over e to the x plus 1 times e to the x downstairs times e to the x dx upstairs. Now I can plug in my substitution. I've got an e to the x dx, which is dz, and everything else is 1 over, let's see, e to the x plus 1, that's z plus 1, e to the x is z, and e to the x dx is dz. So sometimes you can make a substitution first, and that will take something that is not a rational function and turn it into one. This is a good example. From here, you would do PFD, 1 over z plus 1 times z is a over z plus 1 plus b over z, which would mean 1 is equal to a times z plus b times z plus 1. Heaviside will save you from here. At z equals 0, this becomes 1 equals b. And at z equals -1, this becomes 1 equals a times -1. So -1 is a. It's a nice, easy partial fractions problem, which means that your integral 1 over z plus 1 times z dz can be rewritten as the integral of -1 over z plus 1 plus 1 over z dz. The first piece is a micro u sub that leads you to negative natural log of z plus 1. The second piece is just straight up a natural log. And then putting back your substitution, this is negative natural log of e to the x plus 1 plus the natural log of e to the x plus c. And the one thing I would ask you to simplify here would be the second piece. So this is negative ln absolute e to the x plus 1 plus what is the natural log of e to the x? How does this simplify? Ooh, it's x. ln and e to the x are inverse functions. So that's what we get here. So this is a fun problem. Yeah, so Quinn asked a really good question in chat. On the test, I'm not going to tell you what method to use. So far in the homework, you can look at the problem as, oh, this is a 7.3 problem. I'm going to do trig sub. Oh, this is a 5.5 problem. I'm going to do u sub. How do you know which method to use? Integration by parts, partial fractions, trig sub, u sub, whatever. How do you know? The answer is our next lecture. So if you look at section 7.5, this is titled Strategy for Integration. The whole point of this section, besides giving you this big ass list of things that you need to know, is to discuss what to do and when. So they say, first simplify using algebra, then look for a u sub. If you don't see a u sub, classify it according to form. If it's got trig functions, try 7.2 stuff. If it's a rational function, try 7.4 stuff. If you have a product that looks like something you would differentiate with the product rule and it doesn't fit into any of those, try integration by parts. If you've got radicals, well, then you're probably looking at trig sub. And if all else fails, rinse and repeat. So next time on Friday, we are going to go through this algorithm together. I will give you my slightly simplified version of that algorithm, which I found works really well. Before I let you go, I want to show you one more of these cool substitutions. I'm not going to finish this problem. I'm just going to start it. So that's the 1 over the square root of x plus the cube root of x. Again, definitely not a partial fractions problem because this stuff down here is definitely not a polynomial. If I wanted to get rid of this square root and just turn this into some variable, I could let z squared be equal to x. Right? I could let z be the square root of x. If I wanted to get rid of this guy, I could let z cubed be x. And if I want to get rid of both of them at once, I need some power of z whose square root is nice and whose cube root is nice. The move here is to sub z to the 6 equals x, which is the same thing as saying z is the 6th root of x, but it's much nicer if you think about it like this. Then you get 6z to the 5 equals, 6z to the 5 dz equals dx. Just differentiating z to the 6 is 6z to the 5. Taking the differential of x is dx. So this is what you have. When you do this, what you get is the integral of 1 over the square root of z to the 6 plus the cube root of z to the 6 times 6z to the 5 dz, which is the integral of 6z to the 5 divided by square root of z to the 6 is z cubed plus the cube root of z to the 6 is z squared dz. And that is now a rational function. It's improper, so you'd have to divide, long division, to get started from there, and then you can do some partial fractions. So these are called rationalizing substitutions, substitutions that take functions which are not rational functions and turn them into rational functions. And they're fun. So from here, long divide, then some PFD. I won't do it because we're out of time today, but these are fun problems that I like. They show up in your study guide, they show up in your homework, so you might expect something like this on the test. Not necessarily this, but something of this nature. Okay, so look at the study guide problems, look at the homework problems. If there's anything you'd like to talk about, I have an office hour today from 1 to 2 p.m. Otherwise, you can always send me Canvas messages. You can chat on the Discord, anything like that. You know the drill at this point. Our exam, remember, is next Monday. It is getting quite close. So if you've been putting off studying, it is now crunch time. We are well into crunch time. So you need to be working real hard between now and next Monday to make sure this test goes well. Remember, last fall, the average on this test was 43%. 43. I don't curve. If it comes out to a 43 again, it's a 43. That's how it goes. So you need to make sure you learn this stuff, all right? I promise you I will not overwrite the test. I'm not trying to write tests that everybody fails. I will do my best to tune the test to your skills. That said, you need to show me what your skills are. So please submit the study guide as soon as possible. Show me your written work on that study guide as soon as possible. That way I can start giving you feedback, and I can also use what I see from you to influence how I sculpt the test. But you need to know how to do all this stuff. You need to know U-sub. You need to be able to find areas between curves and volumes. You need to be able to find work, and average value. You need to be comfortable with integration by parts, trig integrals, trig sub, partial fractions, right? You must be comfortable with all of those things. So if there's any place there where you're nervous, you need to come see me in office hours. We can work some stuff out, okay? That's it from me. I hope you guys have a lovely rest of your day. Again, if there's anything you want to talk about, come see me in office hours. Otherwise, I'll see you on Friday when we discuss strategies for integration. That will be our review for the test. Take care.